Hello my dear students, today we are in lecture number 34 of chapter 3, okay, and it is current electricity. My dear students, we have completed in last lecture about the atomic form of Ohm's law. Today we'll proceed for the Ohm's law also. But before starting that Ohm's law, we should discuss about the mobility. Okay, the first topic we are going to discuss here, the mobility, and that mobility will represent by symbol mu. I am B.S. Pandey. My dear student, when we talk about the mobility, we come to the conclusion it is a capability. Okay, it is the capability. Mobility basically is the property of conductor in which the electrons flow, but this property comprises for the charge only. Okay, that is the charge carrier of electricity in conductor. Then you can write the definition of mobility in such a way, it is the capability of charge carrier to drift itself per unit electric field. As you will give the electric field, you will increase the electric field, you will see that the charge particle, that is the electron, it drift with the high speed, and that actually explain the mobility. So you can write the definition, it is the capability of charge carrier to drift itself per unit electric field is considered as mobility. From the definition we got, this mobility is nothing but the mu is, mobility is the drift speed per unit electric field. Okay, you will have the formula for the mobility. It is Vd over E. Do you remember the formula of drift speed, my dear students? Yes, it was E tau by M and divided by this electric field. What was that E? The charge of an electron. E, electric field in which the charge particle move within the conductor. Tau is the relaxation time. M is the mass of an electron, and E again that same electric field. This will be cancelled out, and then you will have the final simple formula of mobility as E tau by M, and this is the mobility, my dear student. Okay, this is the E tau over M. So we are concluding that the mobility is nothing but it is capability. Okay, it is the capability of charge carrier to drift itself per unit electric field within the conductor. Okay, my dear students, the number of questions you will get directly, the value will be given, and you have to find the mobility of charge carrier within the conductor. Now, my dear students, we'll land up to the next topic, and that is the very important Ohm's law. Okay, Ohm's law that you have been studied already in standard 10th. Okay, so the Ohm's law. Can any student tell me the proper definition of Ohm's law? Yes, it is the actually when Ohm was doing an experiment, what he found that if connected a conductor, if this is the conductor, okay, and it is connected by a battery, when he increases, of course this conductor having some property, is inherent property, it was revealed as the resistance. We had discussed earlier about the resistance also, but this particular conductor of certain dimension, and this particular law was given for the certain condition. Actually that experiment was done under certain condition. Ohm was doing an experiment and he applied a potential of 1 volt. Okay, 1 volt. He observed that, remember, the current of 1 ampere. When increase the potential for 2 volt, you observe the 2 ampere current. We are talking about a particular conductor, and this conductor will be considered as the ohmic conductor. Okay, remember. So after uh, increasing the voltage 3 volt, the current was 3 ampere, and so on. It means the ohm was observing there was relation, okay, and linear relation between this voltage and current. Thus that was the V directly proportional to I. Okay, as voltage was increasing, the current also found to be increased, and then ohm conclude for few conductor, because that experiment was done for the various conductor and it was not found the same relation, linear relation, for all the conductor, but for the ohmic conductor, that is the metals, he found that V directly proportional to I. And after each experiment he found that for the different conductor there was a certain constant. He observed V is equals to the constant R I, and famously it is written as the V is equals to IR. But remember, Ohm also do the experiment to find whether this relation hold in all situation, and he find that no, that is not holds for the all situation. We will discuss in very detail about the limitations. Okay, what are the limitation of Ohm's law? But here we can say that V directly proportional to I at a certain condition, and that conditions are the temperature. Okay, the temperature where the experiment was done, the temperature was constant. Okay, if the temperature will change, then remember this relation will also change, that you will obtain this resistance R might be not constant. So the temperature at constant temperature, okay, at constant temperature, if you are writing the definition, that is you are writing in word that law, it is the voltage applied across any ohmic conductor, it is directly proportional to the current developed across the conductor, okay, at constant temperature for ohmic conductor, my dear student. Remember, how this resistance actually varies, we will study in factors that affect the resistance and resistivity, my dear student. But this was the simple Ohm's law. If you will represent this particular law and try to show over the graph, you will find such a relation. It is, suppose it is V is equals to IR. Okay, we have represented this V over the y-axis. Okay, this is on x-axis, and this is the constant, suppose it is the m. Could you correlate this one as y is equals to mx plus nothing but 0, and the equation we used to write for the straight line, it is y is equals to mx plus c, if I'm not wrong. Y is equals to mx plus c, it is the coordinate, the quantity we use on the y-axis. On the x-axis it is the slope, that is the m, and this is the c is a constant. Remember, here you are finding this constant as 0. If you will, this graph started as on y-axis, we have taken here the voltage, so it is the V, and over x-axis we have taken here the current. This is in volt and this is in ampere. Okay, my dear student. Now, if it is C is 0, which is a constant, then the graph should be start from origin, and this will look like this one. Okay, and if this is theta, then this will give you the slope. Okay, my dear student, here the slope, you can write this slope, which is m. This is also known as the tan theta. It is nothing but the resistance. Okay, it is, yes, resistance, the slope tan theta. Remember, this is the resistance tan theta, and if you will try to find out here in this graph, this will give you the current, sorry, the voltage, and this base will give you the current. Here this is voltage. So the tan theta perpendicular by base, here the theta perpendicular is V voltage and the base is I. So you can also find here you are getting the V is equals to I times R. Okay, so in this way, if you are having a question in which it is given the graph which is making 30° and you have been asked to find the resistance, then you can write directly the if y-axis taken as the voltage and this current taken over the x-axis, then resistance will be nothing but the tan theta, that is the tan 30° will be the resistance. Okay, my dear student. Okay, now next. This is the simple nature of Ohm's law. You can say, you can draw this graph as also if I'll ask whether the Ohm's law is valid in this graph or this graph representing the particular Ohm's law, then you can give the answer, my dear students. If this is voltage and this is current. Okay. Now the question, whether this one is representing the Ohm's law. My question is whether this one is representing the Ohm's law. Try to think over about this graph and give me the answer after the lecture, or you can write in comment or in group. If it is representing the proper graph, then for which type of conductor this graph will be. Okay, this one, whether this one is the correct graph. If it is voltage and current, whether this one is correct. This is your origin, this is your origin. Okay, now the third one, I'm representing here the another graph, whether this one is the correct graph. If it is the straight line, whether this one is obeying the Ohm's law. This is the current and this is the voltage. So these are the three diagrams, student. I'm asking in this three diagram from you whether these are obeying the Ohm's law. Okay, this is my simple question. Now we'll move to the section this resistance. I will explain you this resistance and then we'll come to another quantity for the resistivity. Okay, my dear student, I hope that you remember about the resistivity that we discussed in last lecture. Here to explain the resistance, you know very well the resistance. It is the inherent property of any conductor by which it try to oppose the flow of charge carrier within the conductor, electrolyte, solution, anything. Okay, so that is called the resistance, which resists the flow of charge carrier. Now that resistance represented by R, and the SI unit of resistance will be ohm. Here let me do an activity, the simple activity to understand the relation between the resistance and resistivity. Okay, how this is important, an activity. Okay, suppose we are having a conductor, my dear student, this one. This conductor is being connected with the battery of voltage V. The length of conductor is L, cross-section area of conductor A, resistance is R, resistivity is rho. All the things are given. If you will apply the Ohm's law, my dear student, if you will apply the Ohm's law, what you will find, V is equals to, if the current start flowing I through this conductor, then you will write V is equals to IR. Okay, am I right? Yes. Let this equation as the first one. Now I'm going to just cut this conductor. I'm going to cut this conductor in two ways. The case 1, I'm cutting this conductor in this way. Case 1. This is very important, my dear student. Try to understand carefully. The one, in this way we have cut out this conductor. Well, okay, so it is cut parallel to the length of the conductor. Okay, now since these two conductors were connected, not the individual or the isolate, so these were connected, so I'm connecting this to with the conductor, the other conductor. Okay, now what will be the changes over this one? Student, try to understand here the length, whether the length will change due to cutting of this conductor in this way. The answer is no, the length remains same. Whether the cross section area will change? Yes, if it is cut identically, then cross-section area will be half, okay, for both the conductor. Whether the resistivity change, so we have studied the resistivity does not depend upon the dimension, so the resistivity is not changed. Now whether the resistance will change, the answer is yes, it might change, but how change we don't know, so write down R dash. Now about the voltage, since we have given the voltage and these two sections are connected in parallel, so the voltage will be same for both the conductor. Am I right? Yes. Now it is connected with the same voltage V. My dear student, the current I flowing through this conductor, though you have studied in standard 10th that the conductor, the current will divide in both the section for both the conductor. If this current I is going, then I by 2 and I by 2 will move in both the section. My dear student, so you can write here the Ohm's law for any of the section. If you're writing Ohm's law, applying Ohm's law for this particular section, then you can write V. What is the voltage of this conductor? It is V is equals to I. How much I? It is I by 2 times R. How much? It is R dash. So you can find either V by I is equals to R dash over 2. Okay, this is the equation 2, my dear student. Okay, let me continue this equation. If V by I, okay, V by I, what will happen? R. This is the first equation. Now comparing this equation 1 and 2, what you observe, this V by I left side, V by I left side, both are same. So R will be equals to, equating 1 and 2, 1 and 2, you are equating 1 and 2. You got that R dash by 2, it is equals to R. It means R dash will be equals to 2R. So due to change in cross-sectional area, we are not changing here the length. Due to change in cross-sectional area, if you halve the cross-sectional area, then resistance will be double. So you can conclude that this resistance is directly proportional to, so inversely proportional to the cross-sectional area. Am I right? Yes. Here cross-sectional area half, resistance become double. Now the second, we are going to cut this conductor lengthwise in this way. Case 2. If we cut this conductor lengthwise, connecting this battery V, the current start moving I, all the things will be considered. Now these two were connected, so I'm connecting with a conductor. My dear student, here what changes takes place. So the length will be L by 2. Cross-section area going to be changed? Answer is no, it will not change. Now the resistance we don't know. Suppose R dash, resistivity, yes, it will be same because it does not depend upon the dimension, my dear student. Now the current here, the current moving I, and both are in series, so the current remains same. There will be no change in current, and both the section will get the current I. Now could you apply the Ohm's law again for this any one of the conductor? You will find that V. Now what about the voltage? Actually this voltage divided equally in both the section V by 2 and V by 2. For any one, if you will apply the Ohm's law, you will find V for any one, V is V by 2 is equals to IR. I remains same, it is the IR. We don't know I dash. Okay, we are writing here the V by I again. So the V by I, we can write here the 2R dash. Okay, now 2R dash. Suppose this is equation 3, equating this equation 1 and 3 again. 1 and 3. What you are getting here, the R is equals to twice R dash. Okay, it means R dash is equals to R by 2. What happened, my dear students? Try to find the conclusion over here. So we got the conclusion. That if you will change the length, resistance will change, of course, but decreasing the length, resistance also decreasing. It means if you will increase the length, resistance will also increase. It means keeping this cross-sectional area constant. Remember, keeping the cross-sectional area constant, if you are changing the length and length become half, the resistance become half. Okay, it means resistance is directly proportional to the length. Now the second conclusion, resistance directly proportional to length. Here also the rho is constant, here also rho is constant, that is the resistivity. So can we just compare these two equation, and you can write finally conclusion that R inversely proportional to the L by A. And what is the proportionality constant in both the equations? It is rho. It means R is rho L by A, my dear student. And this is the resistance. This is R is equals to rho L by A. I hope that this is not very tough for you, my dear student. Can you write down? I'm wrapping this one. Okay, now my dear student, I'm giving you a very simple question. Okay, a very simple question. We'll solve this question as a classwork, and then I'll give you few homework. Okay, now the question is, you are having a metal rod. This is metal rod. Okay, and this metal rod is connected with a battery of voltage V, and it establishes a current I ampere. Length of conductor, it is L, cross section area A. Okay, I hope you got. Now this conductor is cut parallel to its length, and both the section is being connected end to end like this one. It is being cut lengthwise, by the parallel to the length, and then connected in this way. Okay, in this way, and then it is connected by the source, my dear student. Now the question, which is very important, remember, it is cut parallel to the length and then connected with the source. We don't know the value of source, but here the current is I, and here the current again I. Now the question, what should be the value of this voltage? Okay, V dash, what should be the value of V dash to maintain the same current? To maintain the same current in this circuit, what was the moving here? If you are moving I, then you have to maintain this I. So what should be the voltage to maintain the same current over here? If you can solve, my dear student, try to solve this question. Okay, let me solve this question, my dear student. Now let resistance of this section is R. Okay, what is the resistance? R or R1, because we will use the two resistance. This is R1. So we can write the resistance R1 as rho. If the resistivity is rho, here the resistivity not change, you know, it doesn't depend upon the dimension, rho L by A. Okay, this is the first equation. Now after cutting, what will be the resistance? So the resistance will be, you can write the resistance R2 as, what will be the resistance? Suppose it is R2, and it is the length will be how much? It is 2L. The total conductor we are taking here, the resistance we are finding, the rho L is 2L. What will the cross section area? Here the cross section area will be A by 2. Am I right? So it is the 4 times rho L by A. You can see this is nothing but the R1. So you can write it the 4 R1. Okay, 4 R1. This is the R2. Now for same current, the condition of the question was to maintain the same current. As we know that I equals to V by R. Okay, for both the conductor we can apply this one. For same current, for same current. Okay, so what will happen here? The voltage, it is V over R, resistance is R1, is equals to, here the voltage is V dash, we don't know, and the resistance is R2. Now we can solve here. The V dash we have to find out. So it is R2 by R1 into V, that is R2 is how much? 4R1 divided by R1 into V, that is V dash will be how much? 4 times V. So this is the simple answer. Okay, I hope you got this one. Now next question we are taking. Okay, we can. You will get the number of questions in my assignment. Let me move for the next topic, my dear student. I hope you understand. If you will not understand anything, you can ask in group or you can comment in comment section. Okay, now my dear student, the next topic we are moving over here. It is the temperature dependence of resistivity and the resistance also. Okay, temperature dependence of resistance and resistivity. Okay, temperature dependence of resistance and resistivity, my dear students. We will actually correlate this dependency or represent this dependency using the formula of thermodynamics we have studied in standard 11. Okay, so using the I should refill the using the formula, okay, of which thermodynamics we have studied formula in thermodynamics. If we will try to recall in linear expansion, it was L at any temperature T, it was L at absolute temperature 1 plus alpha delta T. Do you remember, my dear student? Yes, LT, it was the length at temperature T. L naught, it was the length at absolute temperature 1 plus alpha, it was the thermal coefficient. Okay, thermal coefficient of linear expansion. And delta T was change in temperature. If you change the temperature, then how the length would change on the basis of this one. Okay, using this formula we are writing directly, because current and heat we have studied already in standard 11th. I have taught you current and heat both follow the same nature. Okay, so here we can write directly the rho T is equals to rho naught 1 plus alpha delta T. Here the rho T, it is the resistivity at temperature T. Rho naught, here the resistivity at absolute temperature. Alpha is, I can write, alpha is the, yes, could you say it is the temperature coefficient. Temperature coefficient of resistivity. Okay, temperature coefficient of resistivity. And what is this delta T? Here the change in temperature. Okay, change in temperature. And this is not important to write here the rho T, the resistivity at temperature T degree, and the rho naught, it is the temperature. In similar way you can write the resistance also, my dear student. And remember, whenever you write, okay, you can write the resistance also, RT equals to R naught 1 plus alpha delta T. Okay, this alpha actually, my dear student, this alpha could be positive or negative. This is very important. Remember, it could be positive or negative. This will be positive, okay, for metals. For metal, that is the ohmic conductor. Non-metals, it will be negative for non-metals. Like carbon, you can say. Okay, so these are the formula that represent you the temperature dependency of resistance and resistivity, how the resistivity and resistance depend upon the temperature. Now using the graph we will try to show the variation of resistivity, resistance with the temperature for various, okay, material that you have to study, because in board examination such type of question will be asked. So for the first we will plot, I can wrap this one, you can write down. This particular formula will be used to solve the questions, and this one also is very important. You can also write this one, my dear student, as R2 is equals to R1 1 plus alpha delta T. And remember, what is the delta T? Here the R2 is the resistance at T2 temperature, R1 is the resistance at T1 temperature. It means R2 equals to R1 1 plus alpha. Here the delta T is nothing but the T2 minus T1. Okay, so you will solve few question I'll give you for homework or the classwork. Now one by one we are going to plot here few graphs which show the relation between resistance and temperature on the graph. For metal first, for conductors. Okay, so for the conductor, my dear student, you can take the example copper. I'm just drawing this particular diagram using the NCERT book. Remember, you can read the NCERT directly for the copper. But one thing remember, it is not mentioned actually. Every metal has some value of resistance and resistivity even at zero. Remember, if this is the graph of resistivity or resistance with the temperature T, then the graph will not start from origin. Remember, this will start, this is not the graph of voltage and current, remember. So this will be start from here and it will goes like this one. You can see this is not the straight line. Resistance increases as temperature increases. Resistivity increases as temperature increases. It means the resistivity depend upon the temperature for metal. Actually, the resistivity depend upon the temperature only, not on the dimension. We have studied already. Now here, my dear student, this is the simple graph of resistivity, resistance, which is varying with the temperature. And one thing I told you, for every metal, remember, and it is very, very important, there must be some resistance even at zero. That's why this is not starting from origin. Now, the second diagram. The second we will plot here for the alloy. Okay, like nichrome for alloy. And this is the graph. Alloy also have some resistance and resistivity even at zero temperature. This is the rho, the R, and which is varying with the temperature T. Remember, this will be the straight line. I think this will be the very steeper, like this way. And this is the weak dependence. It shows that because you can see this is the very steeper, slowly it is increasing. The slope is very small, and this represent the weak dependence. Okay, this one, this arrow represent the weak dependence or the dependency, okay, of temperature. So this is the graph for alloy. And the third one is for semiconductor. We'll study in chapter 14. That's the very small chapter. This is the plot of rho T, the RT, and as the temperature increases, the resistivity decreases for the semiconductor. You don't have to study for the superconductor, otherwise the graph of superconductor, the graph for the superconductor will be looks like this one, rho T. You will find it goes like this one, but you don't have to study in your syllabus. So this is the dependency of temperature, that is the resistivity and resistance, how depend upon the temperature we were discussing. Now you can solve now few questions, student. Okay, I'm giving you some, and the homework will be, my dear student, solve example of NCERT. I'm writing over here, solve example of NCERT. Which one? So you will find example 3.3 and 3.4. Example 3.3 and 3.4. You will show me in doubt discussion class. Okay, my dear student. So this is all about today's lecture. Thank you very much.